Today, we're diving into the fascinating world of Anatase, one of the crystalline forms of titanium dioxide. It might just look like a bunch of atoms arranged in a pattern, but there's a lot more going on beneath the surface. Let's start by exploring its unit cell and the type of crystal structure it forms. At first glance, Anatase seems to have a cubic arrangement, thanks to its close-packed atoms. That's because it follows a cubic close packing, or CCP. But here's the twist. It's not a perfect cube. Anatase is not a perfect cubic structure because it has a tetragonal crystal system with unequal axis lengths, resulting in a distorted octahedral structure. So even though it looks pretty symmetrical, the geometry reveals a unique twist in its crystalline identity.
Let's take a closer look at the atomic arrangement inside Anatase. Anatase is made up of two types of ions, titanium ions and oxygen ions. Starting with the titanium ions. There's one titanium ion located right in the center of the unit cell. Then 4 more titanium ions are found on the faces of the unit cell. And finally, 8 titanium ions sit at the corners. Now let's talk about the oxygen ions. 2 oxygen ions are placed at the center positions. 8 more are located along the edges. And another 8 are positioned on the faces. Together, this precise positioning of titanium and oxygen ions gives Anatase its stability, tetragonal symmetry, and unique physical and chemical properties.
Now, let's find the unit formula of Anatase. Let's start with titanium ions. There's one titanium ion at the center of the cell, which counts fully as 1. 4 more are located on the faces. Since each face is shared with another cell, only half of each counts, giving us 4 multiplied by 1 over 2 equals 2. Finally, 8 titanium ions sit on the corners, but corners are shared among 8 cells, so their contribution is 8 multiplied by 1 over 8 equals 1. Add them up. 1 plus 2 plus 1 equals to 4 titanium ions per unit cell. Now for the oxide ions. There are 2 oxygen ions right at the center, and since they're fully inside the unit cell, they count as 2 multiplied by 1 equals 2. Then 8 more are on the faces, so like before, they each contribute 1 over 2. That's 8 multiplied by 1 over 2 equals 4. And finally, we have 8 oxygen ions on the edges. Each edge is shared by 4 unit cells, so they contribute 8 multiplied by 1 over 4 equals 2. Add those up. 2 plus 4 plus 2 equals 8 oxide ions per unit cell. So in total, each unit cell of Anatase contains 4 titanium ions and 8 oxide ions, giving us a perfect titanium-4 oxide ratio. Try to guess what is the unit formula, or also known as Z, of Anatase. You're wrong. Even though Anatase has 4 titanium ions and 8 oxygen ions per unit cell, we don't add them to get Z. That's not what Z represents. Z is not the total number of atoms, it's the number of formula units, titanium-4 oxides per unit cell. Close, but still not correct. While there are 8 oxygen ions, Z isn't based on whichever ion has the larger count. That's it! The correct Z value for Anatase is 4. Why? Because the unit cell contains 4 titanium and 8 oxygen ions, which make up exactly 4 complete titanium-4 oxides units.
My turn. Let me explain about the coordination number of Anatase. Each titanium is surrounded by 6 oxygen ions, forming what's called an octahedral coordination. Here you can see the 6 bonds. 4 are in the equatorial plane and 2 are in the apical positions, 1 above and 1 below. This geometry gives titanium a coordination number of 6. On the other hand, each oxygen ion in Anatase is shared between 3 titanium ions. That means oxygen has a coordination number of 3. So, in Anatase, the ratio of coordination numbers is titanium-oxygen equals to 6, 3. Anatase also has different crystal surface orientations, which are crucial in determining how the material interacts with light, ions, or molecules. The 101 facet is the most thermodynamically stable and commonly exposed surface in natural anatase crystals. The 100 plane is less stable but can still be found in certain synthetic or engineered crystals. The 001 facet is particularly interesting because of its high reactivity. It features exposed undercoordinated atoms, especially titanium ions, which enhances its activity for applications that will be explained later.
Hey there, would you like to know more? Yay! Then let's talk about the applications of anatase. One major application is in lithium-ion batteries. Anatase is used as an electrode material because it's low-cost, stable, abundant, and non-toxic. But there's more. Its 001 crystal facets, these are the surfaces perpendicular to the C-axis, favor faster lithium-ion insertion or extraction, which means it allows lithium ions to move in and out more efficiently. This leads to better reversibility, higher storage capacity, and faster charge-discharge rates. That's incredibly valuable than other materials for electric vehicles and large-scale energy storage systems. Another important role anatase plays is in photocatalysis, especially for environmental cleanup. Thanks to its unique electronic and optical properties, particularly its ability to absorb UV light and its high electron mobility, anatase acts as a powerful photocatalyst. It can greatly improve photocatalytic oxidation of organic pollutants in water, helping with high-level water purification as it offers higher efficiency and stability. And it doesn't stop there. It can even neutralize hazardous indoor air pollutants like nitrogen monoxide and acetone. The secret again lies in the 001 facets. These unique surfaces and electronic properties help absorb water and pollutants more effectively, and they also promote better charge separation and transfer, which boosts reactive radical production for pollutant breakdown. Anatase titanium dioxide's nanostructures exhibit strong antibacterial effects against various bacterial strains, primarily due to their high surface-to-volume ratio and carrier lifetime, which are effective on inhibition of bacterial activity. Nanocrystallites with a high oxygen-to-titanium weight ratio are more effective against inhibition of growth of MRSA, indicating that the presence of oxygen species on the surface of nanocrystallites play a key role in antibacterial activity. Additionally, smallest nanocrystallite size demonstrate greater inhibitory effects, with increasing concentrations of titanium dioxides leading to significant growth reduction in MRSA, E. coli, and Pseudomonas aeruginosa.